Hi guys, in today's video we are going to go over classwork 1 for Math 407, which goes over proof by induction and the rational roots theorem. So let's look at the first statement. Prove that 2 to the n is bigger than n squared using mathematical induction. For which n is this true? Okay. Well, first, let's recall that the principle of induction for natural numbers say that we can prove a statement Pn to be true by showing 2 points. The first point is we show that a basis P1, P2, or some arbitrary starting point holds, and 2, we show that Pn plus 1 is true by first assuming that Pn is true. So let's get started. Let's try to find this starting point n. Right, so we'll start with n equals 1. If we take n to be 1, we get that 2 to the 1 is bigger than 1 squared, and this holds. How about n equals 2? 2 to the 2 is bigger than 2 to the 2. 4 is not bigger than 4, so this is wrong. How about the third case? N equals 3. 2 to the 3 is bigger than 3 squared. 8 is not bigger than 9, so this fails. N equals 4. N equals 4. 2 to the 4 is bigger than 4 squared. We have 16 bigger than 16. This is wrong. How about n equals 5? 2 to the 5 is bigger than 5 to the 2. 32 is bigger than 5 squared. This is right. And for safe measure, let's go on to the 6th case. 2 to the 6 is bigger than 6 squared. So 64 is bigger than 36. And this is true. So we can see that it takes, so this statement Pn is 2 to the n bigger than n squared will hold for n bigger than or equal to 5. So with that in mind, we can get started on our proof. The first case is our base case. So as a basis, we'll let n equals 5. Then 2 to the 5 is less than 5 squared. And this is true. Now, the second case is we have to assume the statement is true for the nth case, and then show that the next one, the n plus 1 case, is true. So now, let the statement Pn, so in this case 2 to the n, is bigger than n squared for n equals k, such that we now want to show that the n plus 1 case is true, or in this case we'll show that the k plus 1 case is true. So what is the k plus 1 case? That will be 2 to the k plus 1. But what is the 2 to the k plus 1 equal to? That's simply equal to 2 times 2 to the k by your exponent rules. So 2 times 2 to the k, well, what do we know? Well, we can use our assumption here. We have that 2 to the n is bigger than n squared, so 2 times 2 to the n must thus be bigger than 2 times n squared. Or in this case, 2 times 2 to the k is bigger than 2 times k squared. And this is by assumption. Right? Now what can we do? We want to get this k squared to be in the form of n plus 1, or k plus 1 squared. So how can we expand this? Well, we can say that this is really less than k, well, this is really equal to k squared plus k squared, if we split up the 2k squared. And this is then less than k squared plus 2k. Now why is that? Well, n is bigger than or equal to 5. If we take k to be bigger than or equal to 5, we can see that k squared, or 5 squared is 25, and 2k for 5, so 2 times 10, or 2 times 5 is 10, so 25 is bigger than 10, that holds. Alright, but what do we have now? Well, let's do 3 instead. You'll see why. If we change this to a 3, then this becomes 25 is bigger than 15, and that still holds. Because now we can split up this 3 into 2k plus k, but this is less than or equal to k squared plus 2k plus 1. And since we take k to be bigger than or equal to 5, 5 is most definitely bigger than 1, and this is a true inequality. But we already know what this is by factoring. This is really k plus 1 squared. And now if we look at the extreme ends of our inequality, you can see that we have 2k plus 1 is bigger than k plus 1 squared. And by that, we show that the two steps are satisfied, and then we can write our statement here. We can say that therefore, Pn in this case, 2 to the n is bigger than n squared for n bigger than or equal to 5. And we are done with this proof. So let's recap. We found the end that satisfied the statement 2 to the n is bigger than n squared. And then, using the principle of induction, we let the base case happen. We show the base case is true. And then on the assumption that Pn is true, we showed that the n plus 1th case is true as well, using the assumption and some algebra as well. All right? Now, let's move on to this second statement. Prove that 11 to the nth power minus 4 to the nth power is divisible by 7. Divisibility, we can rewrite this in terms of divisibility notation. This is the same thing as 7 divides 11n minus 4n. Okay. Well, let's go on with our proof then. We first want to show that a base case is true. So, as a base case, let n equal 1. If we let n equal 1, we have that 7 is simply 11 to the 1 minus 4 to the 1, but that is really just 7 divides 7, and that is true. Now you want to assume that the statement is true for the nth case, so let 7 divides 11 to the n minus 4 to the n be true for the n equals kth case, such that, well, what does it really mean for this to be true? Well, let's see that 11 to the n plus 1th power, or k plus 1th power in this case, minus 4 to the k plus 1th power, we can see that, well, if we split up the exponents like we did in the previous problem, we get that 11 times 11k minus 4 times 4 to the k. Okay. Well, in order for us to get our k plus 1, or in order for us to use our assumption, we have to try to think about how we want to simplify this to have some form of 11 to the k minus 4 to the k. We have the 11 to the k, we have the 4 to the k, but they are being separated by these terms out in front. So what we really want to do is we want to introduce a magic 0. So So what magic zero can we choose? If we want to just hone in on this 11 to the k, it's being attached to this 11. So why don't we just add in subtract a 11 times 4 to the k, and then re-add that back because we don't want to change the problem. Minus 4 times 4 to the k. This is our magic zero right here. Doing so, we can group these by we can factor out an 11 out of the first two terms and a 4k out of the second two terms and see that this is equal to 11 times 11k minus 4 to the k plus 4 to the k times 11 minus 4. If we simplify further, the front stays the same, so the first two terms stay the same, and we get that the second term simplifies to just 7 times 4 to the k. Now notice, the first term is 11 times 11 to the k plus or minus 4 to the k, and that's our assumption right here. So this is divisible by 7. As for the second term, this is also divisible by 7 because it's being multiplied by 7 as well. The sum of these two are then thus divisible by 7. So this is divides 7 by assumption. This divides 7 by assumption as well. And then we can simply just say that since the base case holds for n equals 1, and the natural numbers start with 1, we can say that 7 divides 11n minus 4 to the n for all n that are natural numbers. And the proof is done. Okay? So we used a similar thing. We assumed the base case, and then we had to do some clever algebra trick by adding a magic zero, and which allowed us to simplify and use the assumption twice to arrive at our conclusion. Okay? Right. Now for the last problem, we want to show that the cube root of 5 minus the square root of 3 is irrational using the rational roots theorem. Now recall that the rational root theorem states that all possible roots of a polynomial with a leading coefficient of 1 are the factors of the constant term at the end. So, knowing that, let's try to begin our proof. You would think that for an irrational problem, or for an irrational statement proof, we would want to use contradiction. But since we were tasked to use this theorem, why don't we try to come up with a polynomial that allows us to use the theorem? So we're going to first let this number that we're trying to find be some arbitrary variable. Let's call a. In doing some algebra, we can see that this is the same thing as saying 5 minus root 3 is equal to a cubed. Or in other words, minus root 3 is a cubed minus 5. In other words, 3 is equal to, by the binomial theorem, a to the 6 minus 10 to the a cubed, 10 times a cubed, plus 25. And if we go further, we get that 0 is equal to a to the 6 minus 10a cubed plus 22. Alright, so we have our polynomial here, and the leading coefficient here is 1, so we can use the rational roots theorem. So if we let f of x be x squared, or x to the 6th power minus 10x to the 3rd power plus 21, or plus 22, so we let f of x be that polynomial, we can use that by the rational roots theorem. By the rational roots theorem, the possible rational solutions of f of x is plus or minus, so what divides 22? Well, 1 divides 22, it's a whole number, plus, and plus or minus 11, and of course plus or minus 22, right? But hold on, if we try to put 1 in, you can see that 1 doesn't satisfy. We get 1 minus 10 plus 22, that is certainly not 0. If we try 11, this is going to blow up. This isn't going to cancel out the stuff, and this is minuscule. So 11s don't work either. And 22 most definitely will not work. 22 to the 6th power is a really big number, which will outshine this x to the cube power. So none of these work. So we can say that but these candidates don't satisfy f of x equals 0. But however, since we devised this polynomial from this a number, we see that a is a solution, which really means that f of a equals 0. But if f of a is a solution, but it's not one of the contenders by the theorem, a must be irrational. And our proof is done. We simply cite the theorem, and we can use it as sufficient evidence to prove our point, without needing the use of contradiction. I think this would be a good place to stop.